Hi. Thank you so much for the introduction. My name is Kenneth. I'm a master's student at the University of Washington studying computer science, and I was part of the team that helped develop Pinpoint, the electrophysiology trajectory planner and automation tool. It's available on the web and on desktop. So the goal for this talk, I'm hoping to share Pinpoint with some of you guys who haven't seen Pinpoint before, and then for people who have been using Pinpoint in their labs, I'm hoping to maybe show some new features that we have going on. So. To get started, I just want to go over like the ideas and goals of a trajectory planner, which is what Pinpoint is. So there are generally four main goals of a trajectory planner. The first is that Pinpoint tries to provide you with stereotaxic coordinates for your insertions, and this is a way to let you plan where you're going and understand where on the brain you're trying to do your experiments. So when you go do your experiments, you have that information with you. The next goal is to make it easier to learn the brain anatomy and observe or uh, work with different atlases. And so Pinpoint supports many different atlases, including not only just the mouse atlas, but also other species as well. So what you see in this photo is the mouse CCF atlas, and we'll get closer into that later. And finally, third, Pinpoint is able to help you add safeguards and save your experiment information so that you can prevent mistakes, prevent collisions, and figure out where you want to go for future experiments. And finally, Pinpoint is able to connect to your robotic manipulators and help you automate some of these insertion processes to let you focus more on data quality gathering and analysis. So these are the four main goals of Pinpoint. As you can see, they kind of build up the interface. So before we go further, I just wanted to give an overview of what the interface of Pinpoint looks like. Here, as we started on in the center, is the Allen CCF Atlas. You can see the olfactory bulb in the front colored in blue, and the cerebellum in the bottom colored in yellow. Inserted into this atlas, we have two Neuropixel 1.0 probes colored in blue and purple. And the white regions here are the active electrodes, the active channels for recording. For each of these panels on the left side, there are probe panels, which represent which regions each of the electrode sites are in. And on the right side, we can see this 2D slice, which corresponds to the in-plane slice of this purple probe, uh, showing you a view of the 2D slice of the atlas in line with the electrode site. And then at the bottom here, this is the stereotaxic panel information, where it's showing you the surface coordinate and depth inside the brain that this probe is at. So together, these interfaces allow you to effectively explore 3D atlases, plan where you want to put electrodes, um, and get the stereotaxic information you need to go and run your experiments. Instead of just showing you pictures of Pinpoint, I think it's more interesting if I show you how Pinpoint works. One of the like key features of Pinpoint is how easy and quickly you can get started using it as is available on the web. So let's take a look at recreating the IBL repeated site recording. This is a location that is posterior left and ventral from bregma. So somewhere in this back quadrant. Um, let's say you want to do this recording, which maybe you have a target here where you want to go through the visual cortex, through the hippocampus, and have your tip somewhere in the thalamus, let's say in the PO region. And maybe there's like a certain angle to your insertion. This is what a plan would possibly look like. Uh, you can approach it from this exploratory approach where you're looking for putting a target in PO, or you may have read these specifications of where the surface coordinate is and maybe an insertion angle. So let's take a look at how we can implement this. If you want to follow along later on in the video recording, you can launch Pinpoint from the website pinpoint.allenneurodynamics.org. So this is Pinpoint on the web. I'm going to open a keycaster here so you can see as I'm pressing my left mouse and moving it around, I can orbit around this brain atlas. So again, this is the CCF atlas of the mouse. If you're following along, if you press the escape key, it will bring up a help menu, which will show you keybinds that you can use on your keyboard and show you all the commands we can use. I'll be kind of walking through these commands as I work through this insertion. Okay, so going back to the insertion we wanted to do, we wanted to put a probe into the PO region and make it pass through the visual cortex. So one approach to this is to use the search box here and highlight the PO region. So I'm going to search for PO, and it'll pull up these all these different regions. I can select it, and it will highlight the PO region inside the brain. So all the other regions are semi-translucent, and the PO region has now become solid. Next, what I can do is add a probe to a scene and start controlling it. So I'm going to use this Add New Probe button. It'll open up our probe library, which includes several Neuropixel probes and other equipment such as pipettes. So I'm going to use the Neuropixel 1.0 probe, and when I click on it, it will add it to the scene. I'm going to zoom out a little bit just so we can use the scroll wheel to zoom out, and so we can kind of see what's going on. So by default, probes have been added so that their tip is pointed at bregma, which is that little gray dot in the middle. Uh, what we can do now is we can click on the search panel. There's this down button, and we can click on that, and that will snap the probe to the center of the mass of the region. So here we've automatically put it so the tip is at the PO region. This is getting pretty close to what we want, but we want to have an angle and make sure it goes through the visual parts of the visual cortex. So I'm going to rotate the probe to match it, to have it align with the sagittal plane, and then pitch it by 15 degrees off the vertical, which in Pinpoint, we calculate angles from the horizontal. So this will be 75 degrees. So this is getting pretty close. Actually, this is pretty much the insertion we want. Maybe I just want to push it down further, deeper into the brain to cover more active recording sites. So I'll use a Z key to move the probe along its axis, along its depth axis. And we've essentially recreated the insertion. You can see in the 2D slice how we're in the where we're hitting the regions that we want, and we can use the WASD keys to adjust to make fine-tune adjustments here on the positioning. So this is a really easy way we can quickly recreate an insertion by just exploring around and moving the probe around and just seeing what regions we can cover and see where the electrode sites will be hitting. The second way that we can do insertions is also like if you got a series of coordinates from like a paper and you want to try to reproduce it, you can just take those coordinates and type them into Pinpoint. So I'm going to remove this probe and we'll start again using the coordinates from some paper, for example. So to do this, we can first create a probe, and I'll align it again to the sagittal plane and give it a 15-degree pitch. Then what I can do is using the APML DV information, we'll move it over into the coordinates that we need. So the surface coordinate is negative 2000 micrometers and negative 2240. So this will bring me on the APML axis, and then what I can do is press this down button to snap the probe to the dura, and that will basically align it so that I'm now touching the dura. And from here, I can then use the Z key, or I can type in a depth to achieve the desired depth that I want to record at. So maybe I'll just click the Z key, and maybe I'll just make this go a little faster. There we go. So I've used the Z key to get down to a certain depth. And again, this is another way we can recreate the insertion. You'll notice that when I press some of these buttons, the exact coordinates here have changed from what I typed in. And that's because Pinpoint is recalculating your AP and ML coordinates to make sure that the surface coordinate is on the surface of the brain. So earlier, when I typed in those AP and ML coordinates, I was actually still above the surface of the brain. And by pressing this down arrow, I had to shift the probe over a little bit to make sure that it's matching the surface of the brain, the contour of the brain. So that's a quick way of showing you how to do an insertion in two different ways in Pinpoint. Okay, so under the hood, Pinpoint does a couple things for you. We found that the CCF atlas is a poor approximation sometimes for the in vivo mouse brain. And so what Pinpoint can do is help you automatically do a bunch of conversions and transformations on the CCF atlas to give you different stereotaxic information that we believe is more accurate for in vivo. So for example, it can supply you with a 2018 transform. Under the hood, Pinpoint does all this conversion for you, and all you have to do is just worry about the end stereotaxic coordinate system you want to use. You don't have to worry about converting between the two. The other thing I mentioned early in the beginning was Pinpoint's ability to automate your experiments. And this is a key feature of Pinpoint where it can communicate with external tools. So, importantly, what Pinpoint can do is actually talk to robotic manipulators such as SensePex and NuScale manipulators and automatically drive probes around for you depending on your plan. So this is an animation here where on the left you can see a plan in Pinpoint being executed and it's moving in sync with a manipulator in vivo. So Pinpoint is able to basically take your plan and relay this information over to manipulator platforms, including SensePex and NuScale, and we're currently working with Scientifica to get support for their manipulators as well. And Pinpoint can also read in the real-time positioning of these manipulators into Pinpoint so you can visualize them along with your plan. In addition to manipulators, Pinpoint can also take your stereotaxic plan information and export them out to or sync them out to other electrophysiology tools such as SpikeGLX and OpenEFIS, where they can use your real-time stereotaxic information to help inform their visualizations. We're currently working with the Allen Institute to also bring in camera-based probe tip tracking so we can actually take your in vivo probe locations and sync them up inside Pinpoint as well as another way of closing the loop between the manipulators, what you're doing in what you're doing in your experiment, and what you see in Pinpoint. Here's a quick overview of the automation process being done with a single probe. In the background, we have a software known as eFIS Link, which is the core module that talks to the manipulators. This is the communication platform that will relay information from the manipulators back to Pinpoint. So here what we're doing is starting off by adding a visualization probe. This is a probe that will be used to visualize where your manipulator is. You'll connect Pinpoint to eFIS Link and then attach the manipulator, in this case manipulator number 7, to the probe that was just added, the blue probe that was just added. And then we'll enable the automation pipeline, which will be a 4-step process that will guide you as a user through doing an automated insertion. So the first step is to synchronize the position of your in vivo probe with your probe in Pinpoint. We do this by touching Bregma on your rig and then telling Pinpoint that they're now synced up. We can now select a target insertion, in this case, that green line that was inserted, and use the start movement button to automatically have Pinpoint drive your probe to insertion site. From here, experimenters should manually insert the probe through the Dura just to make sure the probe doesn't bend or break. And once you're through the Dura, you can tell Pinpoint you're ready to drive and execute the drive. So something that just happened here is that during that insertion drive, Pinpoint is able to actually enforce a lot of safety procedures and also help with more complicated drive patterns. So what happens is that as Pinpoint is driving the probe, as it sees the probe get closer to the target location, it can slow down the drive speed. And then it can drive past your target location for a specified number of microns, and then drive it back up to your target resting location. These extra steps help prevent dimpling in the brain and also help uh, reduce tissue damage, which will help your recording quality. When you're done with your experiment, you can press the return to surface button and Pinpoint will safely retract your probe up to a distance above the brain surface. Okay, in the background, Pinpoint is developed as a series of modules that interconnect with each other. So at the core, we get all of our data from the open source Brain Globe API. This is a open source library of brain atlases in a standardized format, and this is how we can access and support many different types of species. From here, we take the information from Brain Globe and push it through our Brain Atlas for Unity pipeline, which will convert these Brain Atlas information from Brain Globe into 3D models you can use. Unity is the backing render engine we use for Pinpoint. And you've actually seen this before if you've seen some IBL projects, because the Brain Atlas renderings is actually what is known as Urchin, our project for representing brains and insertions. And so this is the render engine used in some IBL projects. and websites. And finally, when we add in the probes and the automation system, that is what brings you Pinpoint, the full stack of visualization and automation. To access Pinpoint, there are two main ways. Today, I've shown you how to use it on our website that's hosted by the Allen Institute. So that's pinpoint.allenneurodynamics.org. And also, you can download desktop versions of Pinpoint via Steam. The Steam library lets you receive automatic updates to Pinpoint as we push them out. Finally, if you'd like to learn more about Pinpoint and view tutorials, you can go to Pinpoint's documentation website, pinpoint.virtualbrainlab.org. Thank you so much. As a reminder, Pinpoint is an open source project which was developed in collaboration with many people, and we really appreciate their contributions. And please come by at NSFN to visit us. We'll be at the SenseiPex, NewScale booths, and I'll have a poster on Wednesday. Thank you so much.